Okay, so we're recording. All right, so hi everyone. This is the first section after the exam, and before I just get started on today's discussion, I just wanted to say like it's possible that you didn't do as well as you wanted on the last exam, and that's completely fine. And I'm not just saying this to be inspirational or anything, but like I got a pretty bad grade on my first algorithms exam when I took the class, and it's like. And like I'm teaching this course, so like I either fudged my grades or I got better. So you guess which one that is. It's always possible to get better at something. And if you want to put in that effort, I'm always there to reciprocate that and just to help you get better. But like even if you you don't in this class, you don't do as well as you want, it's not like you're locked into whatever skill level you are at the end of this class. Okay. There's always room for growth. Like y'all are still, undergrads, you can get better. And like I said, if there's anything I can do to help you all like understand algorithms a bit more, I'd be happy to do it. So with that being said, let's focus on getting better for the next exam. So I'll switch my pen color so you can see it a bit better. Okay, looks good. Okay, so today we're going to talk about divide and conquer and recurrences. So divide and conquer is a very common thing that comes up when we're doing when we're analyzing certain like algorithmic problems. So the idea, right? Some recurrences like they have the following form. So you want to like see how much time it takes to solve problem n or a problem of size n. Okay, let's call it T of n. So you might break it down into a subproblems where each subproblem is a little bit smaller. Let's say n over b. Okay, then plus. So this is the time it takes like divide it into a subproblems, each of which is just a factor of b smaller than the original subproblem of size n, and then you have like some time to stitch them back together. That's f of n. Okay, and so when we replace f of n with something like theta of n to the d, this is called the master theorem. Okay. So this is, we can apply something called the master theorem to solve this kind of recurrences. It's called the master theorem because whenever you have like a recurrence of this form, you just have one like a master key to solve the problem. So what is the master theorem? By the way, I promised my last section, Smarties, we're at like 5 out of 20. I promised my last section that if I called it Master's theorem, I would add a Smartie because it's not Master's theorem. Master wasn't a person. It's the master theorem for solving these recurrences. Okay, so point that out if I say Master's theorem. It's the master theorem. In fact, if I say it even once today, I will take this number 20 down to 15. Okay, so effectively adding 5 Smarties. Okay, so the master theorem. What does it say? It says that, well, there's 2 steps here. There's a divide step where we divide into smaller subproblems and solve them. And then there's a conquer step where we stitch the divided subproblems back together. Do I have my volume up? Okay. Did anyone say anything while I was talking just now because I had my volume on mute? Okay. Okay, so, all right, someone in chat? Nope, you're good. Okay, thank you. Okay, so, right, so let's think about the cases here. So should it take more or less time if A is bigger? If the number of subproblems, there's more of them, right? If we have a larger number of subproblems, should we intuitively take more or less time to solve the problem? More, yes. Because there's more things to solve, right? That's intuitive. So what about if B is bigger? Should we take more or less time? So we're solving smaller subproblems if B is bigger. So as B goes up, does the time go up or down? You think? When B is bigger, n over B is smaller, right? So when n over B is small, the algorithm runs quickly. So when B is big, n over B is smaller. There's a bit of a trade-off there, okay? So B is like, the division factor of our subproblem. So the smaller subproblems we divide into, the faster the algorithm takes, okay? And it should be clear to you that like, a faster conquer time means a faster algorithm, like just in general, because you take less time to do the conquer step. So overall, you have a less runtime. So let's see how like they might trade off. Okay, so we'll define something called, and so we'll say T of 1 is equal to some constant. Okay, we require this to be true. And luckily, this happens to be the case like most of the time. I should turn off my Slack notifications because I'm going to keep getting those. And I'll turn off my Discord as well. Sorry. When you're a gamer, you always get notifications. So I have to make sure I turn off my Discord before I teach. Okay, so okay, I've taken forever to, let's define C, okay? We're going to define C to be the log base B of A. Okay, which is equal to the log of A over the log of B. This is a change of base formula. Just take it like for granted right now. Then this log over here is any log, okay? So what is C in some sense? If A goes up, does C go up or down? I'm just looking at the two people in the room because I can't look at people through their screens, but feel free to answer in chat. So yes, up, it does go up, right? Because log is an increasing function. Now, if B goes up, does C go up or down? It goes down, right? So what does this mean? If A goes up, then C goes up. If B goes up, then C goes down. It's in some sense a measure of the divide step. If we have larger subproblems, that means B is small. So C goes up because log B is small. And if we have more subproblems, then log A is bigger, so C is bigger. So C is in some sense, it's a proxy for how long it takes to do the divide steps of the divide and conquer process. Okay? And so the idea is either the runtime will be dominated by the divide step, by the conquer step, or both will be interplayed equally. And so let's look at the first case when it's, so we'll say T of n is equal to theta of n to the C if C is greater than D. That is, if you can think of this divide step as like some polynomial like n to the C or something, then that means that polynomial dominates n to the D. In other words, we are dominated by the divide procedure, not the conquer procedure. And if they're equal, then it's just n to the C times log n. This is also, you realize you could also write in like D here because C is equal to D. Okay, so you just have to tack on a log n for reasons we will explore shortly. And finally, does anyone want to guess what happens if C is less than D? What is the intuition here? The conquer step takes most of the time. So what happens here? What is the runtime? Any guesses? Anyone? Okay, I'll get you started. It's n to the, there's something that goes here. Not C, because that's if C is greater than D, right? Here D is bigger, so it's n to the D. Yeah, let me remove this dotted line because it looks confusing. N to the D. Okay, interpretation. If the divide step dominates, then the runtime is determined by the divide step. If the conquer step dominates, the runtime is determined by the conquer step. And if both are equal, then it doesn't matter which one you choose because they're both the same. You do have to add an additional factor of log n though. Okay, so we'll explore this in depth a little bit. So maybe you want to take like a screenshot of this if you're on Zoom, or just like write down the master theorem somewhere because we're about to solve some problems. So in particular, solve problem number 1 and problem number 5. And so we can do number 1 first and then discuss it, and then we can move on to 5. So I've written down a moral over here, which is like, understand, don't memorize. So like the master theorem is like a great example of something you would put on your cheat sheet for an exam, right? So it's not really something that you should commit to memory. Like you should just understand, first of all, when to use it and why it's true. So understanding the argument of like why this happens when C is bigger than D, just understanding the intuition there. Human brains aren't meant to like memorize like just binary information, like in terms of like memorize this formula. You have to understand it, and that way you can break it down into something that you can remember for a longer time. So with that in mind, we're going to start thinking about problem number 1. So the occurrence here, okay, is T of n is equal to 9t of n over 3 plus n squared plus n plus 1. And so let's go back to the master theorem here. This suggests, right, the fact that this is n to the d and like you don't have like lower degree terms. It suggests that basically we can treat this n squared plus n plus 1 as like roughly an n squared, right? Because we can like after some level we can replace it with like 2n squared or 3n squared or something, and then basically just adding a constant factor to the divide step doesn't actually affect anything. It just adds a constant factor to the final runtime. So the idea is we can just replace whatever the conquer step is by the highest order term. So the runtime should be the same as solving just this somewhat simpler problem of just n squared. Okay, so what does the master theorem say? C is equal to log B of log A. I got a question here. It says, can you explain the second part of the master theorem? What happens if C equals, oh yes, so good question. We're gonna answer that very shortly, okay? Why do we need the log n? Well, we're gonna see that in this problem. So we're gonna solve this problem in 2 ways to kind of illustrate why the master theorem is true. But does everyone understand intuitively why this is true and this is true?
Can you, hey Vishnus, can you explain real quick, like for C and D, like the conquer step, which is like, when you say dominate, is that faster? Is that running?
No,
faster
dominates
runtime?
means it takes longer. So when you say
Oh,
a term dominates the runtime, if you have n squared plus n, that's theta of n squared, because as you get to really high asymptotic numbers, that n is really outweighed by the n squared. Okay.
gotcha. So for this first case of the master's theorem, it would be the C conquer step that's dominating. It takes longer.
Yeah, that's right.
Okay, all right, thanks.
Yeah, no problem. So by the way, if I have time, I'll tell you about my calculus teacher's Ross-Perot theorem. But anyways, okay, so it has something to do with asymptotics. I think it's pretty funny. But okay, so right, so C is log B, sorry, log sub B of A. What is B in this case? Remember, A is the number of subproblems and B is the factor we divide the subproblems by. So what is A and B in this case? What is B? 3. And what is A? 9. What is log 3 of 9? It's the power we have to raise 3 to get 9, which is equal to 2, right? Now, it just so happens that D is also equal to 2. So C is equal to D. Which case of the master theorem are we in? We're in the middle one, where the divide and the conquer are like roughly equivalent. And so we have to add a factor of log n for reasons we don't know yet, but we'll shortly prove. So what is it? N to the D or N to the C log n. Both of them are equal to 2, right? Because this is the middle case and log n. So this is our answer. But we kind of lucked out here. This is a recurrence that was in the right form for us to use the master theorem. So what if it's not, right? So let's practice on this example to see how we might deal with such a case. So what we're going to do is something called recurrence trees. Okay, we draw a circle, like a tree, where we like label each node by the size of the subproblem. Okay, so this is a subproblem of size n, which breaks into 9 subproblems, each of size n over 3, right? And each of these further breaks into like 9 subproblems of size n over 9. Okay. And then so on and so forth. Okay. And so we do this all the way until we reach subproblems of size 1. And there'll be a certain number of those, and then we're done. Okay. So this is the tree, and in the right margin, we're gonna have like, we're gonna sum up the work done at each level. Okay. So that is, we're gonna sum up the amount of time we do at each node. So at each node, we just conquer the remaining subproblems. We split up into smaller subproblems. Each subtree does the work for those subproblems, feeds the answer back up the tree, and then say this node over here does the work for like to conquer all of these over here. Okay. So the work we're thinking about is the work it takes to conquer the subproblems. That is to stitch the solutions together. So for example, for merge sort, what is the time needed to stitch two like sort of sub arrays? Well, you just look at each element and you like pick the shortest, like you keep a pointer on the beginning of each array, and then you just increase the pointer until like you slowly start adding elements in increasing order. So you look at every element once roughly, and then that takes time like order of n. Okay. So how much work is done at level n here? It's n squared. Okay. That's the conquer step. So we do n squared work at this level. How much work do we do at the level directly below it? Well, how many subproblems are there? 9, because we took one subproblem and grew it 9-fold. And what is the size of the subproblem? N over 3, right? And so it's n over 3 squared. And what you should notice here, okay, is that this 9 cancels with this 3 squared. So we get n squared over 9 times 9, which is just n squared. That's no coincidence. C is equal to D. So it's no coincidence that if you raise 3 to this power, you get this number. That's the case C is equal to D. Okay, and that's why we define C to be log sub B of A and not like A over B or like square root of A over B or something like that. Okay, so this is a very, very calculated idea to take log sub B of A. Now, what about at the next level? We might see another coincidence. So how many subproblems are there? 9 subproblems grow 9-fold again. So we have 9 times 9, 81 subproblems, each of size what? What is the size of the subproblems now? N over 9, because we take n over 3 and we divide by 3 again. Again, there's no coincidence here. 9 squared is equal to 81. We again get n squared. And I think this is enough for us to see the pattern that all of these are going to be n squared. The next is going to be like 729 over like whatever the square root of 729 is, n over 27 squared. So that cancels out again. Okay. So you do n squared at each level, and then you do all the way to the bottom level. So at each level, you do n squared work. Now, question here is, how many levels are there until we get to constant? Okay. The idea is, how many times do we have to divide by 3? Right? How many times do we have to divide n by 3 to get equal to 1? Okay. So basically, n divided by 3 some number of times is equal to 1, right? So 3 to the k equals n. And so k is equal to what? Yeah, log base 3 of n. Okay. And the way you remember this, right? I mean, if you have like a standard tree where each time in the subproblem you divide by a constant factor, right? You remember that the height of the tree is like log the number of like the problem at the top, because like you have a tree over here, right? You draw an actual tree, and you remember the height of any tree is a log, because this is like a log, you know. Anyways, that's enough biology for now. But okay, so right, so that's where we get the log n from. Okay, so there's n log n levels. At each level, you do n squared work. So now we have theta of n squared log n. We don't have to put log 3 because remember log. If you have a log right here and it's like not in an exponent, the change of base formula says that if you just change the base, you acquire a constant factor. Okay, so don't worry too much about the base of the log unless it's in an exponent, which we're going to see shortly is important. Okay. So now let's think about problem number 5. I should have created another one. Any questions about this one though? Okay, so we're going to talk about number 5, which is like T of n is equal to 2t n to the 1/4 plus 1. Is that right? Yeah, that's the problem. Okay. So again, we cannot use the master theorem, or not again, but we cannot use the master theorem here. So we shouldn't become too reliant on the master theorem and instead exercise this technique of recursion trees. So that's what we're going to do again. So at the top, you have something of size n. Then you create 2 subproblems, each of size n to the 1/4. So what happens to a problem of size n to the 1/4? We create, again, 2 problems for each one. But what is the size of the problem now? It's not n to the 1/4, but n to the 1/4 to the 1/4. What happens if you take an exponent to the exponent? Those exponents multiply, right? So formally, a to the x to the y is equal to a to the x times y. So you get n to the 1/16. Okay, you have 4 of these problems, and so on. Okay. Now, let's calculate the amount of work done at each level. What work is done at this level? Well, you notice that the conquer step does not depend on the size of the subproblem. It just takes constant time to conquer the subproblem. So the amount of work done here is 1 step of work, right? Because there's only 1 subproblem and it takes constant time. How about n to the 1/4? How about the n to the 1/4 level, like level 2? How much time does this take? Yeah, it takes 2 because there are 2 nodes, each does 1 unit of work. And then the next one is 4 because we double again, each does a constant amount of work. The idea here is the amount of work done at each level depends not on the size of the nodes, but the number of levels, or sorry, the number of nodes, okay? Because each conquer step is just constant in the size of the problem. So we do 1, 2, 4, ... And then we reach the bottom where we like have like some constant. Actually, it can't ever be 1, so some constant here, okay? And then we have like 2 to whatever level this is. Okay, like let's say this is the 0th level, this is the 1st level, this is the 2nd level, and so on. Okay, so first we're going to show something here. What is like 1 plus 2 plus 4 plus ... 2 to something, right? What is this summation? K goes from 0 to n, right? What is this summation equal to? Well, I'll just tell you right now, it's 2 to the n plus 1 minus 1, which is theta. It's just 2 times 2 to the n. So it's theta of 2 to the n, okay? Plus minus some constant factors. In general, if you have like some common ratio and you're taking the sum of this geometric series, like let's say it's r, the sum of r to the k from k goes from 0 to n is r to the k plus 1 minus 1 over r minus 1, which is, again, it's theta of r to the n. So the moral here, right? When you have like a geometric series where every term is like some constant number times the previous term, geometric series they're dominated by the last term. That is, the sum is going to be theta of the last term. Here, the last term is k is equal to n, so 2 to the n. The summation is like theta of 2 to the n. Here, the last term is r to the n. The summation is theta of r to the n. So I'm not going to prove this because this is not like calculus, right? If you want to see a proof of this, you can ask me at office hours. You can consult any good online resource about it. This is a pretty standard proof, which is available online. It's not easy, but it's like, you know, it's widely available. So the important thing here is when you have a geometric series, like when you're trying to sum up the work and each level doubles the amount of work, the last level dominates the runtime. Okay, you can just say it might as well just be theta of 2 to the level. So we have our runtime here. The runtime is theta of 2 to the level. But wait, we don't know at what level this ends. Okay, that's tricky. We don't know at which level this recursion, this recurrence ends. So let's observe something. Okay, so what do we have? We have n. We have n to the 1/4. We have n to the 1/4 to the 1/4. Again, you multiply the exponent, so you get n to the 1/16, n to the 1/64, and so on. Can we think of an expression for this? This is n, like at the kth level. Let's say this is the 0th level, the 1st level, the 2nd level, and so on. At the kth level, the size of the problem is n to the 1/4 to the k, because we multiply by 1/4 every time we go down a level in the exponent. Does this make sense? Does anyone have an objection to this? I will write it bigger just in case people don't understand what this is. N, okay, to a power, which is 1/4 to the level. Does anyone disagree with me on this? Does anyone like disagree and not want to challenge? If you don't, you can like just private message me and I can explain it again. Okay. If you have a question later while we're working on something, don't hesitate to ask, okay? So the size is 1/4, n to the 1/4 to the k, and we stop when this becomes like some constant factor, and then we can just brute force the problem at that point, okay, let's say. So the idea is we stop at the level k, where n to the 1/4 to the k becomes a constant, and taking the log, okay? So remember, we want to solve for k here in terms of n. We want to bring this out of the exponent. The way we do that is by taking the log. So we take the log. Let's say it doesn't matter what log we choose. Let's say we choose log base 2 to be consistent, okay? What happens to the, so n to the 1/4 to the k equals the log of a constant. The log of a constant is again a constant. And so, oh dear, let me create some more space here. Okay, right. So now like log of n to any power, you bring the power outside the log. 1/4 to the k times log of n is equal to some constant. So now we solve for k here. So we get for the k is equal to like some constant times log n. So k is equal to the log base 4 of this. The constant factor doesn't matter. It's log base 4 of the log base 2 of n. Okay? Any questions here? Do we see how I got this?
Yeah, can you go over that step real quick? So you took the log base 4 of the left side, and then on the right side, you also did
This step?
Yes.
Yes. So remember the log base a of a to the k is just equal to k. Log base a is the opposite of a to the like whatever. Okay. So it undoes the exponentiation. So we bring the k out of the exponent. And on the right hand side, we're just tacking on a log 4 to this expression. Okay.
Okay. Is that multiply? Like, is that log 4 or of that? Okay.
Yeah. Right. So it's an iterated log, which is a really small number.
Okay. Thank you.
In terms of x. So, yeah. Okay. Yeah. Good question. So any other questions about this? Wouldn't it be 4 to the k is equal to log n over constant? No, because this is 1/4 to the k and you're multiplying it onto this side. Okay. So so it's not over constant. Okay. All right. So Sorry. Okay. Someone had entered the room and I was wondering if they were. Okay. Anyways, so now we have K. So now we just take 2 to the level. Okay. So now we take 2 to the level is our runtime. The level at which we end is equal to log base 4 to log base 2 of n. Now, I said previously that it doesn't matter what log you take in general, or like a lot of the time, because like, you know, log base a of n is like some constant times the log base b of n, right? But this constant factor doesn't matter when it's like not in an exponent, but when it is in an exponent, do you agree that 2 to the 2n and 2 to the n, these are not like theta of each other, right? Can we see that? Because this is equal to 2 to the 2 to the n. So this is 4 to the n and this is 2 to the n. And these are not theta of each other, even though 2n and n are theta of each other. Okay, so you have to be careful here. So the fact that this is a log 4, okay, and not a log 2 is really significant. So you do have to preserve logs sometimes. Basically, whenever you're putting a log and you're undoing it with an exponent for some asymptotics problem, you have to pay attention to the base of the log. Okay. So, all right, let's with that in mind, let's solve this. So 2 to the log 4 of log base 2 of n. What do we get over here? Well, this 2 doesn't necessarily undo this 4 because they're not the same base. The trick here is to write this 2 in terms of 4. How can you write 2 in terms of 4 in some exponential form? 2 is equal to 4 to the what power? Well, 2 is the square root of 4. So 2 is equal to 4 to the 1/2. Okay. So we rewrite this as 4 to the 1/2 to the log base 4 of log n. And we remember that when you have an exponent to an exponent, these exponents can multiply. Okay, so we can write this. In other words, we can pretty much just swap this exponent. So 4 to the 1/2 to the log base 4 of log n is 4 to the log base 4 of log n to the 1/2. So let me write that down. This is the same thing as saying this I just swapped the order of the exponentiations because this holds because like this really is the product of these two exponents. And by the commutative property of multiplication, you can just swap the order of the exponents. Does that make sense? Like this black magic that I did over here? Okay, so now can we undo the log? Yeah, because we have a 4 here and a 4 here. Remember, exponents undo the logs in the same way that logs undo the exponents. So 4 to the log base 4 of log n just gives us log n, and we still have the 1/2 on the outside. So we write log n to the 1/2. What is anything to the 1/2? Well, it's like taking the square root. That's exactly what 1/2 is. So we get square root of log n. And that's our answer. Now here it doesn't matter if you write 2 or 4 or whatever, because if it was like, we can just use the change of base formula and we pull out the square root of a constant. So asymptotically, that doesn't change anything. Okay, so our final answer is the square root of log n. Any questions about that? I'm sure there's a lot. I will say right now that this is probably one of the harder recurrence problems you can expect to see. I won't just say it's like the hardest right off the bat, but if I see something harder than this on a test, I will make sure to advocate that they don't put it on a test that's timed. Okay, so yeah.
Do you mind just going from the top, like the n to the 1/4 to the k? Like how do you start with the right hand side, right? You said it equal to log 2 of a constant. I don't understand where that log 2 of a constant is coming from.
Yeah, where do I get the log 2, right? So the idea is I want to like take n to the 1/4 power enough times that I get to a constant in terms of n, right? And so how do I get to that constant? How do I solve for the number of times I have to do it? Well, I write it like this. So this is in the exponent, right? This 1/, like all terms involving k are in an exponent right now. I want to
Mhm.
isolate them. And the way I do that is by taking the log. And when I take the log of an exponent, the exponent comes outside of the log and becomes a factor. And then I can just use like standard mathematical, like algebraic tools to solve for the
okay,
Okay.
I think I see. So you from the very beginning, you started with n to the 1/4 to the k equals a constant, where that constant is like the number of levels that we're trying to find, basically, right?
Yeah,
To this, okay. And
right.
then you're just solving. Okay, all right. I
Right.
think I got it.
Okay, cool. Okay. So notice, right? If this had not been like a log base 4, right? We wouldn't have needed to add this like 1/2 step over here. And we wouldn't have gotten square root of log n. We might have gotten log n squared, or we might have gotten 4th root of log n, or just log n, right? So there's a lot of details in this problem that are kind of like hiding in this solution. So for example, what if this 1 over here was not a constant? What if this was like 1/2 instead of 1/4? What if this was 1, or what if it was 4, or something like that? So there's a lot of things you could ask here. Each of which gives an interesting problem, and each of which I would recommend you try to solve, because like my philosophy for like practice problems is, if you want like a new practice problem, take an old practice problem and change something small about it, and then try to see how the solution will change. If you can do that enough times, you'll understand pretty much every aspect of the solution. And then when you won't have to ask like, why do we do this? You'll understand exactly why we have to do that and what changes if some assumption is different. Okay. So the moral here, okay, and I believe I wrote this in my exam tips document, which is on my website. The moral is to change small aspects of the problem. And then like solve again. Okay. So that's a very good strategy that I employed as a student. I'm still a student, but I don't, take exams. But it's also helpful for like research. Like you try to redo a proof and change some small assumption and see how the proof changes. Okay. So it's a generally useful tool. So, okay. So sorry we spent so much time on these two problems. I thought they were particularly, informative. So that's why I decided to do those two. You should do the other ones on your own time. But right now we're going to go to problem number 3, which is basically we're thinking about this problem of counting the number of unique binary search trees. And how might we build an algorithm that does that? Okay. And so this might seem kind of intimidating. Like you could say like, okay, where are all possible places I could put the 1, and then all possible places I could put the 2 after I place the 1. And that gets a bit like, that gets a bit annoying and tedious. So there's an important observation you can make here. You note that for any binary tree that I give you, and for any like numbers, let's say 1, 2, 3 that I give you, you can take this binary tree and realize that there's exactly one binary search tree. That is, there is exactly one numbering of the nodes that makes this a valid binary search tree. And the reason is, why are binary search trees useful? Well, let's basically you draw a dot at the bottom of every node, okay? I think this is called like the in-order traversal, where you like start around the left and then like you draw like a thing around the tree, and you don't cross any of the edges. And basically every time you hit the bottom of a node, so we hit the bottom of 1 here, we hit the bottom of 2 here, and we hit the bottom of 3 over here, that gives you a 1, 2, 3. And so like 1, 2, 3, they have to be in order. So there's a very specific order you have to put the nodes in. So if I tell you that the binary tree looks like this, then the only binary search tree that comes out of this is this one. If I tell you the binary search tree looks like this, well, let's just think about it. Can 1 go over here? Well, no, because we can't put 2 over here because it's to the left of 1, right? No value to the left of a node in a binary search tree can ever be greater than it. So 1 can't go there. How about 3? Can 3 go over here? Well, no, 3 cannot go over here because that would require either 1 or 2 to be over here. And that is less than 2, or sorry, less than 3, but it is still on a right-hand side node. So we see that like only 2 can go here, and of the remaining things, 1 has to go here and 3 has to go here. Okay, so moral here, okay, is to look for symmetry. Look for symmetry in problems to simplify them. What is the simplification we made here? The simplification we made is that the only thing we need to look for here, right, is the number of valid binary trees with n nodes. Okay, a binary search tree exactly corresponds to each one of these. And so now think about how to like take this fact, okay, and count how many binary trees there are with exactly n nodes. Okay. So in particular, think about like all the possible sizes of the left subtree and all the possible sizes of the right subtree and how you would combine them. Okay. So I'll give you some time to think about that and then I'll go over it. My computer's running low on battery. Does anyone see an outlet that's like nearby? I think that's the closest one, right? 1 minute. Okay. Okay. Again, feel free to ask any questions. Okay, so let's start talking about this one. So the idea, right, is if you have an n node binary tree, how many nodes could be in the left subtree? What is the smallest number of nodes that could be in the left subtree? None. You could have a binary tree that looks like this. There's nothing in the left subtree for this node, for this root node, okay? What is the maximum number of nodes you could have in the left subtree? N minus 1. All the nodes could be in the left subtree and the right subtree would be empty. So this is like the opposite of that, where all the nodes are in the right subtree and the left subtree is empty. Okay, so basically you have a choice from k goes from 0 to n minus 1 for the number of nodes to be in the left subtree. And if there are k nodes in the left subtree, how many must be in the right subtree? So remember, we have n nodes total. K of them are in the left subtree, and one of them is the root. So how many must be in the right subtree? N minus k for the number of nodes in the left subtree, minus 1 for the number of nodes in the right subtree. Okay, or for the root, pardon me. K is the number of nodes in the left subtree, 1 is the root, and then so you subtract from n to get the number of nodes in the right subtree. And so each different value of k gives a different set of arrangements for this binary search tree problem, okay? So basically, we'll call it T of n. Okay, T of n is equal to the sum. We're going to sum all possible values of k from 0 to n minus 1. Remember, k is the number of nodes. We're indexing over the number of nodes in the left subtree. We have T of k, and then we have T of n minus k minus 1. So how do we combine them? Do we multiply them? Do we add them? Do we subtract them? I don't know. What can we do here? And does anyone know? I know you're not required to take combinatorics for this class, but there's a very specific kind of way of thinking about this problem. And it's that for every choice of these T of k arrangements of the left subtree, there are T of n minus k minus 1 on the right. So for every single one of these left subtree arrangements, there's this many right subtree arrangements. And so every like ordered pair of them produces a different binary tree. If that's the case, you have to add like this for each choice of this. So if you're adding something a certain number of times, that's just multiplication. So that's the explanation there. Okay? Does everyone agree with this recurrence? Again, this is not a runtime recurrence as much as it is a solution recurrence. We're going to compute this recurrence, and that's our final answer. Okay? So we can just, I mean, this is a fairly straightforward thing to just, we can just build a function that does this through recurrence. You can also build a function that like, notice that T of n depends on all values smaller than it, like it depends on T of 0, T of 1, T of 2, ... T of n minus 1. So you can go in order, okay? Like you can build an array and store the memory so that you don't have to use recursion. Now that is something called dynamic programming, which we're going to get to. Oh, that was a loud notification, my goodness. Okay, which we're going to get to in a few weeks. Okay, but basically don't think about the details of implementing this. You can just stick it into a standard like Python program. We need to figure out the base cases though. So how many ways are there to like, what is T of 1? A binary tree of size 1? Well, there's only one thing you can do. It's just an empty node. But the real question is, what is T of 0? Is T of 0 equal to 0? A hint is whenever I ask a question like that, it's usually kind of rhetorical or like it's a trick question. T of 0 cannot be equal to 0 because if it was, that would cancel out this k is equal to 0 case, and we would never consider any trees that have an empty left subtree, or for that matter, an empty right subtree. So T of 0 cannot be equal to 0. We just say that there's only one tree and it's the empty tree. Okay, and with this in mind, you could just implement this in a fairly straightforward manner. And you just have to compute this recurrence over here, okay? So any questions about this problem?
Yeah, I had a quick question. So T in this case, that's like standing for like a tree, a binary tree or search tree of size n.
Sure, yeah. The number of arrangements of a binary search tree of size n is dependent on the ways you arrange a binary search tree that's smaller in size.
Okay, and the expression is like T of k times T of that expression there.
That's right.
Okay, number of arrangements, right? Okay, which we're trying to solve, and then the 0 case, right? So what? So I guess that's 1. We just why doesn't 0 work there?
Well, because we're summing k is equal to 0, like right here, right? Well, if T of 0 is equal to 0, then that term cancels out. And we don't consider the possible arrangements where there are 0 nodes in the left subtree and n minus 1 nodes in the right subtree, like this over here. See this arrangement? This would not.
Gotcha.
Okay? Yeah, gotcha. So that's why you have to be careful.
Okay.
Yeah, so, right.
And then T of k is the left subtree, the number range. Okay.
That's right, yeah.
Got it. All right.
Minus k minus 1 is the number of nodes that remain for the right, so.
Okay, all right, thanks.
Yeah, sure thing. Anyone else have a question? I guess not. So if that's the case, I'll just stop sharing and I'll end the recording.